Welcome to True Projects. In this video, we are going to explain about a novel intrusion detection method based on lightweight neural network for Internet of Things. Introduction. The necessity of intrusion detection systems in guaranteeing the security of Internet of Things is discussed. The exchange of enormous amounts of data with external resources makes the IoT vulnerable to intruders. IDS, intrusion detection system, is often used to monitor network traffic and provide an immediate alerting message. Network intrusion detection is a classification problem that can automatically discover and classify potential attacks and threats hidden in network traffic over time. It presents a unique NID technique for IoT that is based on a lightweight deep neural network LNN model and achieves more efficient feature extraction via lightweight units. Objective. To address this issue, we developed a lightweight neural network dubbed LNN, which employs a compressed neural network in the form of 1D convolutional layer, which requires less processing and resources than 2D convolutional layer and 3D. To deal with large parameters, we use the PCA, Principal Component Analysis Dimensionality Reduction approach, which selects just significant feature parameters and skips all unimportant ones. We compare the LNN algorithm to SVM, support vector machine, random forest, and CNN with and without PCA. We are implementing SVM, random forest, and proposing LNN because it is tough to implement all of them. Requirement. To implement this project, we have two kinds of requirements: hardware requirements and software requirements. In hardware requirements, we have operating system Windows only, processor i5 and above, RAM 4GB and above, hard disk 20GB and above. In software requirements, we have Python IDEL with 3.7 version. Methodology. To implement this project, we have designed the following modules. The first module is upload UNSW NB15 dataset. Using this module, we will upload dataset to application and then find and plot number of normal and attack records. To train and test performance of all algorithms, we used UNSW NB15 dataset. This dataset is intrusion data and IoT focused. The second module is pre-processed dataset. Using this module, we will pre-process the data. That is, dataset contains numeric and non-numeric data, but machine learning accepts only numeric data. So by employing label encoder class, we will convert all non-numeric data into numeric data. Replace all missing values with 0. And the third module is PCA dimension reduction. All processed records will be input to PCA, which will select all relevant features and drop all irrelevant features as dimensionality reduction. Reduced features will be split into train and test, where application using 80% dataset for training and 20% for testing algorithm performance. And the fourth module is run SVM algorithm. 80% training data will be input to SVM algorithm to train a model, and this model will be applied on 20% test data to calculate prediction accuracy. And the fifth module is run random forest algorithm. 80% training data will be input to random forest algorithm to train a model, and this model will be applied on 20% test data to calculate prediction accuracy. And the sixth module is run propose LNN algorithm. 80% training data will be input to propose LNN algorithm to train a model, and this model will be applied on 20% test data to calculate prediction accuracy. This algorithm will use PCA reduced and compressed model layers for training and testing model performance. And the seventh module is comparison graph. Using this module, we will plot comparison graph between all algorithms. And the eighth module is detect attack from test data. Using this module, we will upload test data, and then LNN algorithm will predict whether test data is normal or contains attack. Execution. For the execution of the project, we need to open the code folder. This is the code folder, which contains the dataset folder. The dataset folder contains test data and the main dataset. To implement this project, we have used UNSW NB dataset. Importing this dataset contains information of ID, prototype, source, state, etc. This is the model folder. This folder contains pickle and .h files stored, which contains algorithm information. These pickle and .h files can be loaded into the project code during runtime to utilize the train models. This is the main code fold. This is run.bat file. Instead of executing a project in the command line interface, we have created Windows bat file to execute the project. Double click on run.bat file. A graphical user interface will pop up. This is the graphical user interface. Now click on upload UNSW-NB15 dataset to upload the dataset. Now select UNSW-NB and open it. So we can see that the dataset is loaded and the dataset contains numeric and non-numeric values. But machine learning algorithm does not accept non-numeric values. So these non-numeric values must be converted to numeric values and the missing values must be filled with 0. This is the graph, dataset detail graph. On the x-axis, we have attack name and on the y-axis, we have attack count. So here 0 means normal and 1 means attack. Now click on pre-processed dataset. So this is the dataset after pre-processing. That is, the dataset is now converted to numeric values from non-numeric and the missing values are filled by 0. We will get the total dataset record and total features found in dataset before applying PCA. Now click on PCA dimension reduction to reduce features. So we will get the total features in dataset after applying PCA. We will split the dataset into train and test, where training will be of 80% and testing will be of 20%. Now click on run SVM algorithm to train SVM and get its accuracy. After training SVM algorithm, we will get SVM accuracy, precision, recall and F-score. This is the confusion matrix of SVM. So here we can see that x-axis represents predicted class and y-axis represents the true label. So the light green color and yellow boxes contains the correct prediction and the blue boxes contains the incorrect prediction. Now click on run random forest algorithm. After training random forest algorithm, we will get the random forest accuracy, precision, recall and F-score. This is the random forest confusion matrix. X-axis represents the predicted class and y-axis represents the true label. Here the light green color box and yellow box represent the correct prediction and blue box represent the incorrect prediction. Now click on run propose LNN algorithm to train LNN algorithm and get its accuracy. Training LNN algorithm, we will get its accuracy, precision, recall and F-score. This is the confusion matrix of LNN algorithm. X-axis represents the predicted class and y-axis represents the true label. So here the light green color and yellow color represents the correct prediction and blue color represents the incorrect prediction. Now click on comparison graph. So this is the comparison graph. On x-axis we have different algorithms and on y-axis we have the count of the accuracy, F-in score, precision and recall. So here we can see that each algorithm is having different metrics and each metrics is defined by a different color. So here blue color represents accuracy, orange color represents F1 score, green color represents precision and red color represents recall. So we can say, by seeing this graph, we can say that LNN is having the highest accuracy, F1 score, precision and recall than random forest and SVM. Now click on detect attack from test data and select test data and open it. So here we can see in the square bracket we have the test data, and this test data is predicted as no attack detected, and this test data is predicted as attack detected. So by using LNN algorithm, we will predict whether the test data is predicted as attack detected or no attack detected. Now click on LNN training accuracy and loss graph. So this is LNN training and accuracy loss graph. On the x-axis we have training epoch, and on the y-axis we have accuracy or loss count. And here the green line represents the LNN accuracy and the red line represents the LNN loss. And with each increasing epoch, accuracy got increased and reached closer to 0, and loss got decreased and reached closer to 0. We will close this. And the final conclusion of the project is, the conclusion emphasizes the proposed unique NID approach for IoT based on a lightweight deep neural network model. To achieve more efficient feature extraction while minimizing computing cost, the method employs the principal component analysis algorithm to minimize the dimensionality of traffic data and lightweight units. To boost feature extraction, the inverse residual structure and channel shuffle operation are also applied. The NID losses employed in multi-classification jobs to deal with the issue of uneven sample distribution. The experimental findings reveal that the suggested method has great intrusion detection performance and can significantly reduce computing cost and model size. The proposed method has potential to provide a viable solution for intrusion detection in IoT.
Thank you for watching video. For more projects, please visit our website www.trueprojects.in. For updates on latest project videos, please visit True Projects YouTube channel and subscribe.